All right, everyone. So we're going to be talking about the volume by cross sections section of the applications of integrals. And we're going to start by looking at a 3D visualization. So right now what you're looking at is the XY axis, and this is what we're seeing in 3 dimensions. So common wording to these questions is that the that the region between these two curves, is the base of a solid whose cross sections perpendicular to, in this case it'd be perpendicular to the x-axis, are either squares, equilateral triangles, or semicircles. So let's just dissect what that looks like. So any little cross section, any sliver of movement in x, any slight dx is going to be the base of a solid. So in this case, the cross sections make squares. All right, so that one little sliver is a square, but remember that square is going to be different dimensions based on where you are in the area between those two curves, because that distance between those two functions isn't constant. All right, so again, we kind of see this picture here. Well, again, the base of the solid could be made up of squares. Maybe it's made up of equilateral triangles, or maybe it's even made up of semicircles. So the shape that we're actually seeing here, and we can put more rectangles on there, or more shapes on there, is something like this. All right, so there's that shape where the cross sections are squares. Here's if they're equilateral triangles, and here's if they are semicircles. So we get some interesting looking shapes. So the key here is, in two dimensions, we need to understand that we are always perpendicular to some axis, the x or the y axis. That dictates what kind of integral we're doing, whether it's dx or dy. The other thing we need to be very careful of is what shape are we trying to make? Are we trying to make squares? Are we trying to make equilateral triangles? Are we trying to make semicircles? There's also isosceles triangles that we'll look at as well. And the key here to integrating all these is that if you want to integrate any of these shapes, if you want to find the total volume, you need to integrate area. So we need to start wondering, what is the area between these two curves? So, the area, so let's look at squares. If we're going to find the area of a square, let's just say that f was that higher function. So we'll say f of x is greater than g of x. Then the integral, or the area of a square would simply be the difference in height, f of x minus g of x. That gives you this length, depending on what value of x you are. And again, if that little sliver is going to then, oh, we're spinning. We're upside down. There we go. If that little sliver is going to make a square, then that sliver, that f of x minus g of x, needs to be multiplied by itself to find the area of one of those particular cross sections. So in other words, this needs to be squared. That is the area of any one single square, but I need all of the infinite tiny thin squares between, I guess I'll say, A and B. The A and B being here and here, 0 and 1 in this case. All right, so in one sense, that's not too bad. A square is a very simple formula. It's simply the distance between those two functions squared. Again, that's giving you one individual little sliver, and the integral of a to b is finding all of those different unique slivers of varying sizes. All right, well, let's move on to rectangles. That's another one you'll see. Now, rectangles could really just be anything, but what you're going to have is you're still going to have f of x minus g of x, because a rectangle is base times height, and so I'm going to say it's f of x minus g of x times h of x. And the problem with that is, well, not the problem, but what's going to happen with that is that h of x could be a number of different things. They might say it's 3 times this, so then you would have f of x minus g of x times 3 of f of x minus g of x, which means that's your area formula for the rectangle. Or maybe they just say, oh, by the way, the equation for the height is 2x, or the equation for the height is sine of 5x. They could put anything they want in there, so h of x can fluctuate, just be aware. All right, well, let's look at semicircles. This is where things are going to get a little bit interesting, so let me draw those two functions again. Here's f, here's g, there's a, there's b. The thing to be very careful of is, in this case, f of x minus g of x is the diameter. All right, it is the diameter of that shape. So when you make a semicircle, let's look at that. When you make a semicircle, f of x minus g of x is the diameter. Well then, that's still not too bad. How do we find the area of the semicircle? Well, maybe I'll do this. A semicircle is 1/2 pi r squared. And I don't yet have r yet. How am I going to find r? Remember, r is 1/2 of that. So 1/2 of that distance entirely squared. Right? Again, half of the diameter squared. That's the radius squared. And then I need a semicircle, so half of pi radius squared. That will give you your area formula. Right? Again, half of the distance to find the radius, square that radius, pi r squared, but we are making semicircles ultimately, so there's another half multiplying through at the end. Now for the most difficult ones, and this is going to take some geometry. Now this video is pretty much just going to be examples, or deriving the formulas, and then we'll do examples for the next few videos. Let's look at equilateral triangles. For equilateral triangles, again, we've got our f and we've got our g. So this sliver is, again, f of x minus g of x. And let's also just draw a picture of a equilateral triangle for the best that I can do. So this down here, that's f of x minus g of x. Now this is going to take some work. Here we go. All of these angles are 60 degrees, so when I want to find the base times the height, I need to remember that this was 60 degrees since it was equilateral. I just cut this in half, so this is now 30 degrees. And now I have a 30, 60, 90 triangle. And there are some special properties to 30, 60, 90 triangles. So I'll draw that to scale here. This is the 30 degree side. Essentially, there's a formula that says your 30 degree side, the smallest side, call that x. And then the hypotenuse side is going to be 2x. Well, I don't really need that in this case. I just need the base and the height. But this piece right here, the height of our triangle, is whatever this amount is times the square root of 3. So my height is this distance, half of f of x minus g of x, times the square root of 3. So let's put that all together. My area formula for an equilateral triangle in the integral is 1/2 times the base times the height, which is, again, this height. How do I find that height? It is half, another half, of f of x minus g of x. And that's getting multiplied by an additional square root 3. So maybe I'll put that square root 3 up here in the numerator. All right, and we can condense this. We can pull all this out. There's a root 3. There's an over 4. I have an integral of f of x minus g of x squared. And that's our equilateral triangle formula. Now you can either memorize all these or you can derive them on the fly as you need them by redrawing all these pictures. Again, it's probably going to be one FRQ, so maybe it's just worth memorizing or having all these kind of formulas written down before you take that AP exam. All right. Last but not least, you'll have some prompts that say you have an isosceles triangle with the hypotenuse as the base. So let's look at that. If we have an isosceles triangle with the hypotenuse as the base, then what you're dealing with there is a 45, 45, 90 triangle. Now that base, again, is f of x minus g of x. But the question is, what is the height? Well, something interesting happens here. When I cut this in half, I get another 45, 45, 90 triangle. So this distance, half of f of x minus g of x, because I've now got another set of congruent triangles, two congruent triangles inside my triangle, I know that half of f of x minus g of x is going to be the height as well, because angles open to similar sides. So since 45 has that side, the other 45 will be equal to the same side. They are congruent. So that gives us a formula of triangles 1/2 base times height, which is half of the entire f of x minus g of x. And that's it. So once again, we can condense that to be 1/4 f of x minus g of x squared. You can pull the 1/4 out of the integral if you want also. All right, and that's all the formulas we'll look at for this section. One thing to notice is if the hypotenuse is the base of your equilateral triangle, take a look at this formula. And now take a look at the equilateral triangle formula. They only differ by an additional square root 3. All right, so there's not as much memorizing as there might seem. So we've gone through all of the deriving of the formulas. In the next videos, we'll go through kind of each of these assignments, squares and rectangles, semicircles and triangles, and we'll do a few examples of each. See you then.